Let's get started. So what we're going to look at here is a way of doing water quality testing using smartphones, essentially. And the traditional way of doing water quality testing tends to be take the water sample and send it to the laboratory. Pay $100 or something. 2 weeks later, get an answer back. And what we want to do is we want to change that. We want to make it so that you can do this kind of test in the field and get a very fast answer and have a reliable answer as well. So the very first basic thing that we wanted to do was do something to automate things called strip tests. You're probably familiar with these. This one does pH, right? The general idea is you take one of these, do a test, use something like this color card, which essentially tells us what lighting conditions are and things like that, so we can interpret the color of this one. The application we have called Caddisfly tells you we're going to do this test is actually the same. We're going to use this one. When we start the test, the first thing Sam will do here is it will detect this thing, find it, and set the color balance right. So the lighting conditions are right. So we use something called white balancing. So now it's done that. We take a strip test. It changes the color of this thing, and then he actually uses the calibrated application to do an interpretation of that. It finds all the dots, finds the black area, finds the strip, it knows it's a pH test of one particular type, and only one dot that it needs to look for. And when it's done, it gives you the result, which is how much? 6.6. 6.6. So the variability of strip tests is a little bit. So the last one was 6.9. Was the same water. Yeah. So 6.6 to 6.9 is variability of the test itself, right? No, the white balancing should be better than that, right? And we did this for a few reasons. First of all, there are lots of different strip tests. You can do iron, nitrates, phosphate, high levels of chloride, no, there are really no fluoride, as far as I know. We'll talk about that next. But there's a bunch of these. And they're inexpensive, they're distributed, made by somebody else. But we want to, rather than taking a note, writing a note, go home, type it into your Excel spreadsheet, send it to somebody, this automates it to the point where it goes into the mobile phone-based data collection system that we have, that then immediately can upload it to the databases that we use. Right? So that was the first thing we did, sort of low-hanging fruit to get this stuff operating. The only hardware we have to distribute is strip tests you can buy locally with these cards. The rest can go over the wire and internet, so to speak. Next one, there are certain tests that you can't really do this way that we really wanted to do. The first one, Sam and his team essentially invented was the fluoride test. Because there really no good field-based fluoride test. You take a small water sample, you put it into this container as a test chamber, you take off-the-shelf available reagent, the reagent you add to the water sample and it colors the sample, depending on how much fluoride there is in this.
On the enabling technologies, it's spiked sample.
The spiked sample, because there's no fluoride in Stockholm, of any meaningful level.
And
So you will see this color change already.
It's sort of purplish. Right? And then the first version was developed just based on the camera in the mobile phone and the flash. Right? And you start a fluoride sample test. It actually takes 6 photographs using applications, and it goes blip, and then it takes a photograph. It takes a little bit of time between them because we found out that if we took them really rapidly, we heated up the CCD, the actual thing that records the photograph. We heated it up from the flash, and it changed the way it reads colors. So we had to give it a bit of time for it to cool down a bit. Anyway, it takes 6 photographs, it analyzes them, and then gives you a result. What's interesting is that a paper we published in the Science for Total Environment journal, peer-reviewed, shows that this is essentially the same precision as an ion selector device used in the laboratory.
Right on cue.
Yeah. So. So, fluoride slightly below the WHO level, right? Which is 1 part per million. You can also do chlorine for residual chlorine. Good to know if you kill all the bacteria in the thing you're going to drink. And we have a very promising thing for arsenic, which is a breakthrough because there are no good arsenic field tests. It can also be done in a minute. Right? It is. Our chemists in Bangalore are a really talented bunch. They've done some really fantastic work. They took some research that some other people have done on figuring out reagent. They reproduced that work, which actually turned out to be really hard. And once they've done that, they are now making those reagents. Now we look at how to figure out how to get them manufactured at scale. We can also do chromium in this. That's already shown as well. So that's a really interesting model. This thing doesn't scale so well because mobile phones are different shapes, they change a lot all the time, etc. So we built this instead, which is an external camera. There's a camera in the middle here. It's got a couple of LEDs, and then you connect it to the phone by USB. You put the thing on there. The thing is here, we can calibrate this once for all the ones we make because we know what camera is in there, and we know that this thing doesn't have to move around on every phone and all of this stuff. Right? So we're working on that. We know this works. Now we need to figure out what scale should we manufacture. We don't know yet because we haven't manufactured, but it's sort of the same order of magnitude as a mobile phone. Right? So it's going to cost you probably the same or maybe a little bit more than one comprehensive water test, but you can do lots of tests. The reagent costs like, in the cents, area, right? The last one is more for, one more. Similar to this kit, it's much more complicated. We have something working in the laboratory that is very, very promising, but it's still a long way away from a product. It's actually doing E. coli. It looks very good in the laboratory. Our researchers in the lab are completely convinced we can do this. We can detect low levels of bacteria content in a 100 ml sample in 2-3 hours. And that's really interesting. It's going to be sort of a desktop kit as well. It's not something you put in your pocket because it needs the incubator, and power source, and a few things like that. But the idea is we should be able to detect the key indicators for the SDGs for drinking water, bacteria, arsenic, fluoride. We have 2 of them.
Immediately in the field, not having sample the laboratory science, temperature and...
Which is complicated. And you don't have to be a university educated lab assistant to be able to do this work. this can actually, the fluoride tests have been done in Bjelkeman with village women doing the work. They could understand enough of it to actually do a reliable test. 5 minutes, good. Last one is more for agriculture. So this is an electric conductivity test together with temperature, and that's a proxy for how much salt there is in the water, essentially. You don't want too much salt in your water if you're doing agriculture, because you can destroy your crops. And what's important with all of them is we don't do any of this stuff without connecting into an online system, because we digitizing content just to get the answer in the hand is barely better than doing a strip test and looking at it. So everything goes into our system. It produces maps, graphs. This is map of Mali, where water point mapping is done with our phone data collection system called Akvo. 40,000 points have been visited. Photograph, GPS location, fill in the form, is it working, is it not working, what type of pump is it, how many people use it, etc. 8,000 strip tests and 1,000 EC sensor tests were done, something like that, I can't remember, as a pilot project in parallel with this. Right? So the vision here is, 10 years ago these things didn't exist. 10 years from now, they'll be literally everywhere, to the point where every village can have a kit like this and check, is my water safe to drink today, now, as opposed to, in all of these places, no checking is done, right? And then it's a huge difference, right? And the upside is also we will collect the data to the point where we can say whether we really have lived up to the SDGs or not. Because we will have ground level data that we can check all the way down to who took this, what equipment did they use, was it, what time of the year was it, all of this stuff, right? So, questions?
Oh, it's more of a, I can see the next phase of this, which was like, let's say, even in the real-time data collection, you can tell people this is a dangerous water well, this is a safe one, go there instead, for the time being, because this one is still and these alert systems can redirect everything to safe traffic.
Beyond that, the immediate application is my water is drinking. How do you connect to kind of a larger picture in terms of maybe policy implementation and government regulators? So for instance, feeding your data into a Ministry of Water or a Basin Authority, or what's the connection with the government's Akvo manage that connection, or is it your clients more so who take their data and then...
We do partnerships with governments and NGOs around this. So the Mali work is in partnership with UNICEF and the government of Mali. So they work directly with that. We work already in a dozen African countries at national level scaling of water point mapping, and they're all essentially saying, we want these things. When can we have them? And my challenge is I need to now finance it to scale it, which is always trivial. And we're a non-profit organization, but we run as a for-profit in the way that we can't lose money to it. We have to break even, and we do that based on services that we provide. We're looking for the right type of collaboration partners to manufacture, etc.
If I follow to that, probably more so a good question for your partners, but how much do they couple, let's say, the citizen science with maybe an education around policy and what things should be like? You know what I mean? People don't really sort of know something's wrong unless they know it's supposed to be right.
Yeah. At the moment, I don't know the answer to that. We don't do citizen science yet with these tools, because we primarily make this stuff available to government, to NGOs. But you can see once we get up to the volume of making these things and make them easy to use, we could equally sell them to anyone who wants them to use them for their own purposes, to schools, to the local biology club, whatever, right? And then we can start pooling the data together. So there are lots of really interesting opportunities there. At the moment I'm trying to pick the low-hanging fruit, which is going to be a government that says, I want to do 100,000 water tests, right? But eventually we'll do them, not just us, but others will do this safety